Hello students, in this set of videos we're going to talk about probability. Just as combinatorics is one of the favorite subjects for Mr. Dobovich, probability is one of my favorite subjects. The reason though may surprise you a little bit. In fact, probability was one of my most scared subjects back in high school. I always approach a probability problem with trepidation, mainly because when I see a probability problem, one of two things would happen. One, I couldn't even approach the problem, didn't know how to solve it, no idea at all. Second possibility, I got the wrong answer. So either one didn't boost a lot of confidence in me, obviously. It wasn't until the second year of college that I finally took a class called Probabilistic System Analysis that a professor showed me how to solve a problem methodically that would finally allow me an approach that I can use to solve most of the probability problems. And since then, I found it very, very interesting because it can be used in so many different ways. Let's take a look at an example. Let's say two friends want to meet at a train station, and because of the different schedule, uncertainty, and so forth, each person can arrive between noon and 1 p.m. And the first person who arrives at the train station will wait for 10 minutes for the second person to arrive. And if that person doesn't show, then the first person says, well, he or she is probably not coming. Then they will just leave. And we don't know who's going to get there first. The question is, what is the probability that they would actually meet? And let's say this is in the old days where people don't have cell phones or pagers and whichever way that they could communicate with each other in real time. So they just made this arrangement the day before. So if you feel like completely stumped by this problem, that's exactly how I felt when I first saw this. So how would you even approach a problem like this? I mean, it's not like tossing a coin where you have 1 out of 2 chances of getting a head or tail or tossing a die. This is like within a time frame, you don't know when someone's going to arrive, and then how would you quantify something like this? So here's an approach. I'm going to represent the first person, call it person A, that they're going to be arriving anytime between noon and 1 p.m. I represent it as a line segment. Okay? That means person A can be arriving anywhere on this line. Okay? And I'm going to represent person B's arrival time, also using a line, but in the vertical direction. So person B can be arriving anywhere along this line. Okay? Between noon and 1 p.m. So if I make a square using these two line segments, then the area of the square would represent all the different combinations where A and B would be arriving, right? So for example, if I pick this point, let's say, so this point would indicate that person A is going to be arriving sometime certain minutes after noon, and then person B would be arriving sometime later afternoon. And if I pick this point here, for example, that would mean that person A is arriving very close to noon and person B is going to be arriving sometime, say, around 12:45. Okay, so you get the idea. So this whole area is going to be representing all the different combinations of A and B's arrival time. Okay, so I've represented this as a square. I've redrawn it. And for simplicity, let me label this as 0. And I'm going to break down 1 hour into 60 minutes. Okay, so from 0 to 60. And similarly, for person B, this would be 0 to 60. Okay, so this is, again, all the possibilities of the combination of A and B's arrival time. Now, what about the chance for them to meet? Okay. Okay, I'm going to represent the chance of them meeting with a green strip. Okay, so let's say person A arrives right around noon. Okay, now how long is this person going to wait for B? This person's going to wait 10 minutes, right? So that means as long as B arrives between 0 and 10, the two people will meet. Now what if A is arriving 1 minute after noon? Well, that means B better arrive from 12:01 to 12:11, right? Because again, A is going to wait for 10 minutes and no more. And if A arrives at 2 minutes later, then B better arrive in between 12:02 and 12:12. Again, because A only would wait for 10 minutes. So if I use the same logic, I can basically trace out a shape that looks like this. Okay, for 1 minute that A is going to arrive later, then he is going to wait a minute longer for B. Okay, so this strip here, this area, is going to represent if A arrives, that he or she is going to be waiting for the other person, and they would have a chance of meeting each other. Now what about B? If B arrives at noon, B is going to be waiting for 10 minutes for A. And if B arrives at 12:01, then A better arrive between 12:01 and 12:11. And if B arrives at 2 minutes after noon, then A better arrives between 12:02 and 12:12. So similarly, I'm going to have another shape that represents that when B arrives, when A must also arrive in order for them to meet. So in other words, by adding the green shape and the blue shape, that area is going to represent the time interval of, the time of arrival where those two people will meet each other. So in other words, the area that I've just highlighted using purple is the area where A and B will meet each other, whereas the other areas that is unshaded would be the area where A and B will not meet. So how do we calculate the probability? So the probability of A and B meeting must be whatever area that is circled by the purple line divided by the total area of the square. Well, that's pretty easy to calculate, right? That's just simple geometry. Well, the total area, let's calculate that first. Using the units that we have is 60 times 60, so that's 3600. And for the purple area, it's probably easiest to use the triangle formula and actually subtract out the white area, the white triangles. And we have two of them, right? So each of these area is equal to 1/2 base times height, right? And since there's 10 units here, so that means the remaining units is 50. So it's 50 times 50 times 1/2. That's for one of the triangles. And for two triangles, that's going to be times 2. And that's going to cancel out that 1/2. So the area of the white triangles is going to be 50 times 50, which is 2500. Okay. So that means the area of the purple shape is got to be the total area subtract out the two triangles. So that's going to be the total area 3600 minus 2500, all divided by 3600. Okay, giving myself a little bit more space here. So that's going to be equal to 1100 over 3600. And I can cancel out the two zeros, so 11 over 36. And this is roughly equal to 0.8. 31. So the chance of them meeting is roughly 31%. So in this case, what seemed to be a very unsolvable problem initially, turns out if we approach it methodically, that we are able to find a meaningful answer. Okay, so in the subsequent videos, what I hope to show you is that by analyzing probability problems in a certain way, we would have a pretty sure way of arriving at an answer.